Slope fields help us to solve differential equations in a geometric view or graphical manner. And if we're looking to solve differential equations through an analytical view or symbolic view, then we have the separation of variables. Sometimes we can't separate the variables, and if that's the case, we can still approximate the numerical solution to a diffie-q by something known as Euler's method. All right. Now, with Euler's method, the idea basically is that if we have a diffie-q and we have an initial condition, then we can overall come up with an idea of what a value near the initial condition of the function would happen to be. Think back to the very beginning of calculus when we started our rules for differentiation, and at some point you were given some kind of curve. All right, and you had that curve, and you had to find the equation of the line tangent to the curve at a certain point, and we knew that that was from the derivative, and it was connected to point-slope form. So let's just say that we were interested in whatever, right here. This is some x equals a. All right, and so at that point, we know what f of a happens to be. All right, but we were more concerned about, like, what about this other value, b? All right, we'll put b right here. All right, so b is up there. What's an approximate value for f of b? Let's say that we could not find it from the original function. All right, well, we could use the equation of the tangent line. All right, so we would draw the line which is tangent to the function at x equals a, right there. All right, and that would allow us to come up with the equation of that function in point-slope form. And then if b was fairly close to a, then that meant that the curve and the line that was tangent to the curve were still fairly close together. And that meant that if we could calculate the value of the line at b, well, that blue dot would be very close to the tan dot. In other words, the approximation would be quite close to the actual value. So we're basically taking this idea and building off of it. All right. So what Euler's method basically said is, all right, let's just say that we have the slope of a curve, the diffie-q, all right, and we have an initial condition. Then can we sort of recreate the curve using that slope and that initial condition and come up with an overall approximate value for a point near the initial condition. All right. So again, let's just say that we have an initial condition and we have the slope of the line tangent to the curve at that initial condition. In other words, we have dy dx. Okay. So what we're going to do is we're going to kind of draw the tangent line. Notice the curve is not here. All right. We'll draw the curve in a moment. So we draw the tangent line, and we're interested again in, say, like if this is our a. All right. We're interested in some b value right here. Okay. So the problem is the curve is it's going to start separating from the tangent line rather quickly. So instead of having the tangent line way out here when in fact the curve is doing something more like this, all right, what we're going to do is we're just going to use the tangent line for a little bit of time. Okay, so we're going to, instead of having the tangent line going all the way out here, we're only going to use the tangent line during that line segment right there. Okay, and now what that allows us to do is now we're going to create another tangent line segment, all right, where we're going to start from the point where we left off, okay, and remember we still have the slope of the tangent line, right? Now our new point is somewhere right over here, all right, so notice that that tangent line is a little bit steeper. So we're going to use the tangent line slope and our new point, and we're going to come up with another line segment. Okay, now our two line segments are closer than if we just had one line segment. All right, so and the thing is, we can go even further than that. We could break it up into the area, the distance between A and B. We could break it up into 3 segments or 4 segments. There's no actual limit of segments that we can break it up into. And so what ends up happening is we have this bunch of segments which are ideally fairly close to the actual curve itself. And that's what's going on with Euler's method. Can we recreate the curve similar to what the actual curve happens to be. Again, it's just an approximation. It's not the exact value, but it's something that works. Okay. Now on the AP exam, you're only going to be responsible for going through 2 iterations. They're not going to ask you to do more than that. It'll take up too much time. But we'll look at these examples in the next video.